Welcome to the weekly M-Cube seminar. Am I on? Yeah. So, today we have Piotr Smolarkiewicz, known to many of you. Peter has a PhD in physics from the University of Warsaw. What year was that, by the way?
1980.
1980. Yeah, and then he's been a scientist here since 1981, and he's now our senior scientist emeritus. And from 1990 to 2007, he was affiliated collaborator of Los Alamos National Lab. And from 2013 to 2019, he was an ECMWF consultant. Since 1996, he served on the editorial board of the Journal of Computational Physics. And before this, a 3-year term as the editor of Monthly Weather Review, altogether processing over 1,000 papers. So match that in terms of AMS journals. Peter has conducted numerous successful research projects in many interdisciplinary applications of computer science. Here's a partial list. Meteorology and atmospheric sciences, mathematical physics, physics of fluids and plasmas, mechanics, astronomy and astrophysics, mathematics, and interdisciplinary applications. And that's just a partial list. Today, Peter's talk is titled Richardson Preconditioners for Elliptic Problems in Numerical Models of Weather and Climate. Peter.
Thank you. It's not crowded, but you are all my colleagues, so it's very nice that you came. It has been a while since I was in this room. So about this work and this presentation, we didn't have to involve Richardson, but I thought at some stage that actually Richardson deserves more credit for the things people are doing right now and attributing to Alexei Krylov, whose paper was never published in English, and so on. So on your left-hand side. On the left-hand side, you see Zbigniew Piotrowski. Some of you may remember him. He did his PhD at NCAR. This was cooperative thesis between the University of Warsaw and NCAR. And Zbig spent some years here. And then later, he got the postdoctoral fellowship at NCAR through IMAGE. And he came here too, spent 2 years. And then he had the idea, to do the parallelization in a vertical. This is still not popular approach, I believe, in meteorology, to parallelize codes in vertical. And he did. Actually, it accelerated the code quite a lot. And because of this, he had to parallelize three-diagonal solve for vertical inversion of matrices. Once he did this, it creates opportunity to do full alternative direction implicit algorithms, which is like an inversion in all directions. And this opened up new opportunities for improving elliptic solvers. And I get to this to it. So there is one kind of I found, preparing this talk a while ago, I found in some curious facts. So when you take like data from Web of Science, the record of Web of Science from 65 to now, and take a topic advection scheme, and 2 journals, Monthly Weather Review, which is historically the journal who was the forum for presenting numerical methods, and then Journal of Computational Physics. statistics are comparable. Like you have a public 260 publications in Monthly Weather Review about advection schemes, about 641 in JCP, but JCP has a much larger audience. So they are comparable. But when you go to Elliptic Solver, this total of publications in Monthly Weather Review with the topic Elliptic Solver is merely 18, where...
How many of them are yours?
And yours. So, and 1/6 of it, i.e. 3 publications in this 18, is from MMM. This is, and of course in JCP you have 7,000 citations, 18, so there are order of magnitudes differences. So bottom line is, this illustrates that the topic of elliptic solvers is like an ugly duckling in our community. It's not popular. We don't talk about this. I don't know if this, why, but this, especially that there is lots about the data assimilation, and there is a close relationship between elliptic solvers and matrix inversion. Those are just people, different languages, maybe different designs, but close ideas. So I want to point out what really I want to convey, because once we start going to some technicalities, times fly, then comes to conclusions, and then there is no time. So I tell you what I want to convey. And think about this as thesis. So Richardson published his paper about the solution of elliptic problem by augmenting it with diffusion equation. But more generally, you can think about his idea is that to augment elliptic boundary value problem with a transient problem that converges to the elliptic boundary value problem, like time, the pseudo-time, goes to infinity. And what I want to show that this type of thinking is just more general what Richardson did in 1910, but it is practically advantageous when dealing with complex systems of nonlinear PDEs. And next point is that I want to convey and document or illustrate is that Richardson preconditioners improve efficacy of Krylov solver, which are the main working horses nowadays in solving elliptic problems. And I explain a little bit what they are and how they work. And so they improve efficacy of those solvers, especially for all scales atmospheric problems, making them, those solvers, universal toolbox for a broad range of complex tasks. In other words, the concept of the suite of preconditioner is practically superior to the concept of super preconditioners based on, e.g., spectral methods or multigrids. And the reason for this is very simple, because I wrote spectral preconditioners, I wrote multigrid preconditioners. When you go to those type of preconditioners, and the problem has complex coefficients, not difficult, variable coefficients, which is typical in weather codes, then when you have a spectral preconditioner, use spectral method, in principle, you have to expand coefficients of the problem in a Fourier series. When you do it, you have to multiply Fourier series. It's getting complicated. The same is with multigrid, because when you use multigrid and you have a complicated variable coefficients, you have to multigrid coefficients. The same thing. So there is a lot of work. And actually, I have colleagues who design multigrid preconditioners to our Krylov solvers in finite volume module of ECMWF code, and work fine, reduce number of iterations, but cost the same or more. This is the problem. And there is one thing that touches upon the culture of the community. There is a new terminology, new trends, fashion, that people refer to assess the convergence or convergence of those methods based on the degrees of freedom. Like how many, and actually it came out from the referee of this paper, and I show you an example that degrees of freedom is mean how many grid points you have. So think like you have 1 billion, right? So depending upon the convergence rate depends on those degrees of freedom. And I'm saying, no, this is not the case. And I show you that it really depends on a spectral composition of your problem. So you have to think about this physically, not just like mechanically how many grid points I have. I may have 2 different problems with the same number of grid points. One will converge fast, another won't. It depends on the composition, spectral composition. Okay, now, so what is preconditioning and why we need it? The Krylov solvers, maybe you heard of this name. This is those are they are also called like conjugate gradient methods. They were invented by the first paper was Hestenes and Stiefel in mid-1950s, and then it became industry. There were lots of them. The idea is that really those are methods which are based on the variational method that minimize like if you would solve the system like your diffusion equation, like take the Richardson scheme, how this well converges depends on your pseudo time step. If my time step is too small, it converges very slow. If it's too large, it doesn't converge at all because it's not stable, it's noisy, and so on. But those methods, they work on residuals, on errors, and they minimize the errors. So they have optimal convergence. This is the point. This is what mathematicians like. They can prove theorems, and they have this, if operator is proper, you have the optimal convergence. And convergence depends on the so-called condition number, and condition number is formally the ratio of the largest to the smallest eigenvalue of the problem squared. Now, when you think in eigenvalue matrix, right, of course, because eigenvalues is, if you know them, you can diagonalize the matrix and the inversion is trivial. Now, the thing is that when you think physically, this is in other words, condition number is the ratio of the longest to the shortest wavelength represented in the system, square. So, and the conjugate gradients have a convergence rate, those methods have a convergence rate proven, which goes like a square root of the condition number. So basically, like proportional to the ratio of the longest to the shortest wavelength in the system. This physical view is approximate, especially for the short wavelengths. But the same like with the diffusion equation when you do von Neumann stability analysis. With the short wavelengths, you have some cosinuses, sinuses, and so on. When you go to long wavelengths, it's basically physical wavelength. Okay. By the way, so why do we need this preconditioning? Because the optimal convergence rate may be too slow. When I have a 40,000 kilometers wavelength one way, and in vertical, say, 400 meters, condition numbers comes as a 10 to 10. So even with the optimal convergence rate, you have to do 100,000 time steps to reduce the error by E factor. So it's extremely slow. So something must be done, and preconditioners are tricky, artful ways to solve part of the elliptic problem such as to improve convergence of those methods on the remaining part that needs to be solved. There was a paper in 1997, 26 years ago, when we addressed, this was Bill, Joe, and myself, and we addressed exactly the same problem. We didn't continue then because parallel computing came, and this parallelization of three-diagonal inversions were impractical at that time. This is one of those 3 papers. Now I have to do this. So I am not going to tell you where it comes from, but basically what I am doing, I want to illustrate how those elliptic problems in atmospheric applications, how they look. What do they do? So you have 2 kinds of equations and two kinds of ways of finishing with the elliptic problem. One is if you have soundproof equations like an elastic, Boussinesq incompressible, or Dale-Duran pseudo-incompressible equation. They all have a convergence constraint which is derived or motivated analytically from asymptotic analysis. So then you have a term like this here. So this is, for instance, like for an elastic or incompressible, there will be just the divergence of some rho v is equal to 0. And one point I want to make, that in all those formulae that you will see, this nabla is nabla. This is not, nabla dot is not divergence. What makes divergence are those are metric, this is Jacobian of metric transformation, the definition of V as opposed to physical velocity U, and so on. Those are details, but the gradient is not necessarily nabla. Strictly using nabla, because this is only in Cartesian system of coordinates. No, very few or very small scale models only work in Cartesian coordinates. Typically we use some transformations, so there is a difference between the nabla and divergence and actual operator. Okay, so now when you have constraint like the 0 divergence, it translates to elliptic problem for the pressure perturbation or pressure, depending how model is written. So this is this guy here. Yes? This is pressure. This part is known. This is explicit part of the predicted velocity, and those G's and C's, those are matrices of 3 by 3 matrices of known coefficients. Those C's are related to semi-implicitness. Imagine you do Coriolis implicitly. You want to have like at n plus 1 or at n plus 1 plus n divided by 2. You take a 1 from y equation, stick it in an x equation, and you finish that you have both in each equation, like in high school. So those are C's related to semi-implicitness, whereas those G's, all the G's and G tildes, are related to coordinate transformations or metric terms and so on. So this is simple and fairly straightforward. There is a thing about the Durand's equation that there is a heat source in this system, and it is included into the elliptic problem. But if you are smart enough and can write or model the heat source as a divergence of something, then you can put it together with the right-hand side of the problem in an easy way under the divergence. Because note that this thing, okay. Now, the compressible systems are more complicated. First of all, there is no holy recipe how to design elliptic constraint, because it doesn't come from theory, but it's basically a way of assuring that your your numerical approximation is stable for large time steps. So there are different ways of doing, and different people do it. In our case, we just use the DDT of the gas law to derive the pressure equation. And when you do the DDT of the gas law, you have a d rho dt, and the d rho dt from mass continuity is related to the divergence, and the divergence is related to pressure gradient and so on. And so there is a heat source included, because ddt may be equal to something. You can write your gas law not in terms of P equals rho RT, but pi equals some product of rho and potential temperature. Just the same thing. So this is, of course, so in this case, elliptic solver is more complicated because it's a sum of 3 different solvers, 3 different divergence constraints with different weights that are known. Those psi L's or A star, they are known. You can derive them. And there is an extra term, which is Helmholtz term, that comes from the d phi dt, it's pressure variable. And this is too complicated. Both notations are too complicated to use them in further focus on preconditioners. Therefore, we symbolize this, whether it's this operator, I mean for the compressible system or soundproof system, we write it L of phi minus R equals 0. This is symbolism. So in this case, R is everything that depends on the explicit part, and L of phi is just 1 over rho, this nabla dot G rho, and that's GTC grad phi. Right? So this is artifact, but this is how we write it, and the people who deal with matrix, abstract linear algebra, they have usually AX equals B. This is symbolism. Okay, why this thing doesn't want to move? This is the oh no. I've been told that you can. Yeah, I know that something will go wrong. Oh. Yeah, okay. So now we are getting to the point. Oh, wow. So what we use, it's standard. There is nothing new about this. Those algorithms are known from 50s. And a particular scheme we use is a so-called generalized conjugate residual K, which K means it's restarted. You do some internal chain of the length K of some sub-iterations, and then this is where this comes. The original paper was 1983. But you can actually interpret it. You can derive all of this from a Richardson iteration. Take for a moment, just focus on this part and think for a moment that P is identity operator. So I have d phi d tau is L of phi minus R. This is exactly, and this is what Richardson did. He took a problem L phi minus R, which is some Laplacian type of operator equal to some source, and he integrated in this tau, which is pseudo time, right? Because it's not a physical time. But you can extend this idea. It doesn't have to be a diffusion equation. It can be, for instance, a damp oscillation equation. And the damp oscillation equation has still keep in mind that P is equal 1. Then there will be another term, which will be d2 phi dt square plus 1 over some scale t, right? And this thing. This was introduced by Dufort, I believe, Frankel. Frankel in mid-50s, and he called it second-order Richardson iteration. And by the same token, you can go to more and more terms. And when you do this, there is a physical interpretation to it that actually, like when you just do simple Richardson iteration, the only way to equalizing lack of balance that you are seeking, the elliptic problem, it's a balance statement, is to relaxation through the diffusion. But if you add extra term, the second derivative, you have already oscillations, waves. So there is additional means of spreading information over the grid when you do those iterations. And a very simple experiment to do is to code a regular Richardson and the second order Richardson, and you see there is a significant increase in the speed of convergence. And you can go farther and farther. When you really go very far with those terms, I coded it such that there is arbitrary number. And the biggest I used was 100, just for a heck of it. When you go to, what was I wanted to say? Yes. When you go to many, many terms, you can start thinking about this, that really you are trying to find optimal representation of the pseudo-temporal derivative from the Taylor series expansion. This is what it is. So you are as close to the analytic solution as possible. And the point is now that what is this P? This P is preconditioner. This is exactly what this talk is about. This is this little part. All the talk is really about this. So the preconditioner is the little trick that makes those convergence even faster. And so the sense, here is actual algorithm written. It's simple. You can derive it yourself by, for instance, if you wanted to take simple Richardson iteration, you work on residuals, or you minimize the future error in certain norm. So there is a so-called residual, which is actual value of L of phi minus R if it's not 0. So this is, you have some guess phi, you calculate it, this is your residual. But having this iteration for phi induces iteration for residual error. So you can minimize it and so on, and you find the optimal convergence. And the other, so those are schemes of the type of minimum residual, conjugate residual, and so on. And if you minimize it in a norm which is product of solution error and the residual error. Solution error is actually phi minus phi exact. And this is not computable, because if you know the solution error, you add it to your, to your guess and you have an answer. But luckily, if your operator has certain property, it's referred as a symmetry, but if you talk about the differential operator without any discretization in mind, this is self-adjointness. What it really means that if I have L of phi and I multiply by psi, so I have psi L of phi integral over entire domain. This thing is symmetrical self-adjoint if it's equal to phi L of psi integrated over entire domain. This is what it is. And this is really integration by parts. And when you integrate by parts, there are boundary terms. So the Laplacian has the properties, that normal Laplacian, that it's self-adjoint, but given that the boundary terms vanish, that the sum over boundary terms vanishes too, otherwise you have vanished. This is why it is so important to get the right boundary conditions when you solve elliptic problems. And so the virtue of residual schemes that work minimize those iterations in terms of residual error is that they do not necessarily require cellular jointness, but they require ellipticity, which is definiteness of the operator. But and those that are minimized in ER norm, why this is ER is a norm? Because when the operator is self-adjoint, ER sum of product of ER is the same like your operator, square root of the operator acting on E times square root of the operator acting on E. So this is a norm. But it has to be self-adjoint, otherwise it won't work. And so this is basically it. And now we introduce somewhere this preconditioner. In this case, this is we call a left preconditioner. And when we predict residual errors and minimize it, preconditioner is something that wants to invert your residual error, because L of solution error is L minus 1 of R. R is L of E, of solution error. So if you have a way of improve or find from your residual error estimate of the solution error, then you accelerate the whole problem. So what we really do, this is now it comes to what we really do with this stuff. So the very simple realization of preconditioner is using, this is preconditioner, this, oh gosh. You see it, this thing here. Why this thing is arrow outside the picture and not an arrow? Must be artificial intelligence. Okay, so this is all what we are talking about. And the simplest thing one can do is a regular Richardson iteration. So not variational, not minimization, just regular, standard, fixed time step integration of the problem with this approximation of your operator and the residual error that you already know from minimalization. This is not well known, it's ancient, and it leads to so-called polynomial preconditioners, and they are on very limited value. Because you really, this precondition does, it smooths out residual error in high frequencies or high wave number. So short numbers on a grid. So it's like a turbulence closure or something of this sort. Okay, so the next very popular preconditioner is something that is many atmospheric models use it, even if people don't think about this in this lingo, is that horizontally explicit and vertically implicit Richardson iteration. So think about this, that I find this E, so those are different iterations. Once you move to the preconditioner and iterate, those are iterations that have nothing to do with iterations in a main Krylov scheme. Those are like, and typically those iterations we do 1, 2, 3 max. And there is a reason for this, and I will mention later. So here we say, okay, I have my P, which is approximation of this original L operator, and then I say that, okay, in a horizontal direction I use the explicit scheme for the prediction of error, but in a vertical it's implicit. So therefore, I move this thing to this side, and this forms three-diagonal problem for the rest, which is explicitly known. And this was historical standard in ULAC, and this is broad use. Another step, you can go further, is going from this, like a standard Richardson iteration, is to take diagonal term in a Laplacian, make it implicit. You don't have to code it like this, because you can take, if you have a, oh gosh. No, now I did something bad. Oh no, it came back. Okay, so you can, if you coded this, you can just add and subtract diagonal term that is at I, right? At the grid position I, you can add and subtract, and then so you are subtracting explicit and adding implicit, and then you again move everything at this mu plus 1 to the left-hand side, and you have another diagonal problem. In this case, it's implicit. You go with the time step to infinity, and then whatever comes out, then the result is that this result from the time step with infinity weighted with the previous one, which is equivalent to having some special time step. One thing is that this also involves like a normalization by the diagonal term. This thing is basically, can be taken as a Dufort-Frankel, but it's also known as a Jacobi, line Jacobi preconditioner. And now comes the fun. This is, you can do the same things with the alternative direction implicit. So the famous Piesman and Rochefort 2D ADI. So you do it like a first, I do horizontal part explicitly and vertical implicitly, and then I flip opposite or whatever direction. And then there is a third. This is Douglas 3D ADI. And you can do it with like 3 steps, one first through X, but Y, Z, and so on. And the key, I mean, there is no difficulty in coding those things. The whole difficulty in this business is tridiagonal inversion, or parallel tridiagonal inversion of the one-dimensional problem, because they are all composed from this. So when this big, this parization in a vertical, it opened opportunities for do this. And there is probably, in a word, 3 known ways of doing this. One is Powicki algorithm. There is a Russian, Terekov, person like this. He has some different way of doing this. And there is a guy in New Mexico, I think it's Albuquerque, had a paper in JCP. He uses some kind of approach that he adds, makes more calculations, goes 2 streams, but can parallelize because of this. What this Powicki algorithm does, the essence of it is you take a simple formula, for instance, like this, and you dissect it into little pieces, pre-compute everything that can be pre-computed at the beginning when you start those precondition iterations. And then there is only, it minimizes exchanges between the processors. This is what it is. Okay, so this is the thing about the theory. This is no more equations. I don't know what this does. You see, it doesn't go. Maybe oh, okay. This was this little circle that helped. So really the value in this talk is not those formulas, but the results. Actually, results are very interesting. So I will show you, I will attempt to show you the results from baroclinic instability on the sphere, global, then thunderstorm, which is Cartesian problem with the moisture and everything. And at the end, problem like a kind of abstract problem from is now the global domain with 23 kilometers in the vertical, and then 360 by 180 by 48 grid points, and 16 days simulated time with time step 100 seconds. Now, on the top, from 2022, you see the solution after 8 days, and at the bottom on the 8 days. 8 days was the time standard for DCMIP model intercomparisons. When people did baroclinic instability, they look at the behavior at after 8 days. I am showing this because this is on a grid that was used typically then in those tests, 128 by 64, so this is about 9 times smaller problem.
But not on the sphere.
On a sphere, yeah.
So that long.
Yeah.
Okay.
This is coarse, very coarse. So I'm showing this that if you remember this type of solutions, then don't be surprised that those look a little bit different. This is the point. And the contour interval is 4 kelvins. Those are isentropes on the surface. Oh, no, wrong way. So here is the reference run, and the results are after 16 days. Yeah, the 8 days is when the baroclinic wave steepens, so nonlinearity starts taking over. But 16 days is when there is a transition, the system transitions to geophysical turbulence. And in those intermodal intercomparisons, they were not interested in this later stage. So the upper one is a reference preconditioner, which is reference is this line Jacobi, Dufort-Franco. And what you see, the solution, well, is mostly in a northern hemisphere. At the bottom is one with the vertically implicit Richardson, which is very typical. The characteristic important result, important difference is that in a lower case, the instability develop on the southern hemisphere develops much faster than in the other case. And there are discussions in literature whether this development of in southern hemisphere is physical or related to some mesh imprintment, truncation errors, and so on. It could be physical. There are physical arguments. Nonetheless, we know that if you run spectral code, then this doesn't happen after 16 days. This instability develops much, much later.
The grid is exactly the same between...
Yeah, everything is the same. And when something will be different, I will point it out. It's identical. The only difference is preconditioner. This is the only difference. So what you see, the mesh here develops much sooner. But when you look at this, at the upper picture, and look at the arrows on the southern hemisphere, they are not straight, they are a little wavy. So you don't see development of southern hemisphere only because the contour interval is too large. In both cases, it's 8 kelvins. If I would make 4 here, it would be unreadable because of the mess on the upper hemisphere. Okay, this is not the end. I don't know. And now you have those two preconditioners. One is XY ADI, XZ ADI, this is top, and another is XYZ. So this is this Pisman Rochefort and Douglas, or something, if I remember correctly. Now when you look at those arrows, the solution on northern hemisphere are very close. I mean, the fine details, but this is the same solution. And what is important that on the southern hemisphere, the arrows are flat. So what this thing shows that the preconditioner, I didn't say yet who is faster, but can change accuracy of your solution. And this is because those ADI preconditioners or direct inversions, they act in a long wavelengths. This is this element of understanding problem in spectral space. They build the balance of the elliptic problem in a long scale directly. You basically integrate this thing directly. I must be doing something wrong. Okay, here is the table. And I don't want to go through it because it's tedious. But what you first, from 0 to 5, you have those different preconditioners. And the first, like from 0 to 3, it's basically you have a no preconditioners, you have a Richardson, Jacobi implicit in XYZ. This means this line Jacobi. This is what it is, the standard. But after 2, I am changing distribution of processors because for those ADIs, the solution depends also on distribution of processors. So when you, just for information, right? So the point is like this. Here we have ADI in XZ, ADI in XYZ, and those iterations, count of iterations, what you see, there are two numbers. Because the system is actually nonlinear, because there is a coefficient, full theta in front of the gradient, pressure gradient, and it's a part of the solution, so there is one outer iteration that first you predict one coefficient explicitly, then you solve the elliptic problem, and then you use, and also this gives you new temperature, and then you use this new coefficient. So that shows you how it iteration from the first and the second iteration. And the key is, of course, times to solution, and it looks like ADI in XZ is the fastest. It is, well, it's not exactly the fastest because this line Jacobi in this case takes 1 minute less. However, as you remember, the ADI is accurate, whereas the other one is not, because it develops this instability. So they are at the same cost, and then, but one is more accurate. So the next one is like increasing number of processors, and the next one, this 3C and so on, is doubling the grid. Doubling the grid, going from 360 by 180 to 720, 360, time step goes smaller. It shows basically how it parallelizes. It doesn't scale perfectly, but it scales. This is the point. No. And now, when you take exactly the same problem, but at orography, and this is just the solution for the same XYZ, the same that you see, so this lower picture from the last. Then it's a basically general circulation you start seeing, because there are mountains. This is initial condition along the surface, isotropes along the surface. This is result after those 16 days. And then the winner definitely is this ADI preconditioner in XZ. It takes the less time. This is it. Now there is a problem. This is from Joe Clamp, Thunderstorm, except it's slightly modified. It's inviscid. So that in original problem there is a bubble, and there is a diffusion. Here there is no diffusion. This is not on the sphere, this is on a Cartesian grid. And when you now look at the same statistics for different preconditioners, it tells you that it doesn't really matter. Actually, the cheapest is no preconditioner, whatsoever. Remember that those Krylov algorithms, the variational algorithms, they are effective. They are pretty fast. So the question is, and the question actually was raised by the referee of the paper, says, so this goes to this number of degrees of freedom. This problem has the same number of the degrees of freedom like this is 720 by 360 by 48, like the problem on a sphere. And behavior of the elliptic solver is very different. And the solution is actually insensitive to preconditioning. The question is why. So this comes to this issue of the physical interpretation of the condition number. On a sphere, you have longest wavelength, 40,000 kilometers, shortest in a vertical, 500 something meters, whatever it was. But anyway, the condition number, the ratio, the longest to the shortest wavelength supported on a grid is 410 to 10, while the same ratio in tornadic storm is 400. So this explains the difference in those behaviors. So it's not about the number of the degrees of freedom, but about the spectral composition of the problem. You can convince yourself in a very simple way. Take a simplest of those algorithms, like conjugate, steepest descent, or minimum residual. This is like taking Richardson iteration, straight Richardson iteration, and finding time step from minimization of those into those two different norms. If your right-hand side is specified as a single Fourier mode, you get the exact solution with this algorithm in one iteration, because it will give you time step that resolves just this one mode. This is example, this is from the magnetohydrodynamics. It's a silly problem, 3D, this cross-section in a vertical. There are two membranes that are flapping in time. And this was invented at the occasion of Niels Veddy's PhD. We tried to figure out how you do boundary conditions when you have moving boundaries. But it turned out to be useful, and here we also have introduced like a magnetic field. There's a toroidal field between the two membranes. So when the membranes go close, the field is this torus or donut gets squeezed. When they spread, it gets spread. And when they come back to the initial condition, depending upon the strength of the magnetic field, you get the you get some hysteresis or not. But in this case, this is like a moderate magnetic field, so it comes back to initial problem. Now when you look at the statistics, how it behaves, and now there are two elliptic problems in a system. One is for pressure, and one is for divergence cleaning in the induction equation. So this shows like iteration for B, iterations for U. And in this case, the problem is smooth. Everything converges very fast. The same number of iterations is not sensitive to, especially for magnetic field. There are some differences in velocity. I think this is all, except for conclusions. Yeah. So, what we really got is that the GCRK solver, which is very practical because it's not non-symmetric, does not require self-adjointness, with a suite of Richardson preconditioners maintains computational efficiency for all scale problems and becomes a universal tool for a broad range of complex tasks. And this universality owes to the increased accuracy in a large scales. And we'll come back to it at the end. And organizing classical stationary solvers under the idea of Richardson it's not necessary to do this, but it's theoretically justified and practically advantageous for programming. When you think in terms of matrix inversion, you have to have discretization. So you are starting thinking about how you will invert matrix after you have matrix. Here you don't have a matrix. You don't have to have a matrix. You just know the problem, and you can, from physical arguments, you can derive those accelerations to the solvers. So difficulty is not developing the suite, it's in the coding of its members, but in mastering the parallel diagonal inversions with Neumann or periodic boundaries. The preconditioners, of course, yeah, I didn't tell you everything. I would need more time. Include free parameters like the pseudo time step, how you specify it, the number of iterations. So pseudo time step in preconditioner is determined by the convergence of the preconditioner iterations. And the number of iterations is reduced to necessary minimum. So for those ADI algorithms, you use single pass through the matrix inversion, one time step. Why? Because preconditioner, you take a simpler operator. In you saw those terrible elliptic equations. Preconditioner is without cross terms because it becomes like a simpler Laplacian, like a formal Laplacian. And then you don't want to do much more iterations with this because this is really not your operator. So you want to use only a little bit of its property to invert something, but to not cause competition between a preconditioner and a solver. Because it could happen you do too many iterations with preconditioner, but the big solver, the mother, doesn't like it, and she will try to fix it. This is the thing. Yeah, so this is what it is. Now there is an exit condition. The holy standard is like to machine precisions. But nowadays there are trends actually to go through the codes and use mixed precision so you can accelerate some parts of the code with benefit to like parametrizations or larger grids and so on. So so typically this standard to machine precision is not so fashionable anymore. And like what we use the physically based criteria. The same was in a paper in 97. This was also about the compressible equation. For compressible case, you compare the size of the residual error that you can write that has a sense of divergence or divergence times delta t. Divergence is 1 on a time scale of compressibility. So you can compare this with the actual divergence. So when the error is much smaller than the divergence, then you say, okay, it's physically accurate solution. For soundproof systems, it's you can compare the divergence to the magnitude of the flow. So like divergence times delta t to the current number. And this is the last comment is about the thinking in spectral space, right? No. Yes, one more very important point. So with these better preconditioners, when you look at the table, it's actually they don't have much. There is no big difference in time to solution, but there is in accuracy. But also there is a thing that you can use less of those iterations for the fancy ADI, because if you use for those cheap preconditioners or simple, you use less iterations, the code can blow. This is what it is. So this is basically all. And the picture with the magnetohydrodynamic, like if you think only in terms of compressible equations, even if always will solve compressible equations. Sooner or later, we go to space weather, and then you have to know how to solve soundproof too, because magnetic field is divergence-free. Okay. Sorry for being, no, I'm not late, am I?
We have, we'll go into Overtown for questions then. Comments, questions? Peter?
If you could just, your actual tridiagonal solver is still implicit. It can't be parallelized, right?
This is what I am talking about. Yes, it can be. People paralyze those things. Nowadays, you talk to those guys who love programming, who specialize in them, they will tell you everything can be parallelized.
That would be the same as saying you can parallelize a one-line FFT. Okay,
This I don't know.
because they're the same thing. It depends globally on the whole operation. Okay, anyway.
No, but I am not fluent in FFTs, but you can say the same thing about the Fourier regular Fourier transform, right? The same, you could say, because it involves sums.
I'd have to show you.
No, but those things are parallelized, and this is not like there are papers about how people do it. It's how you design algorithm, how much you pre-compute first, and how much information. And there are some tricks also, like you go one way, another way. Okay.
Further questions or comments? If not, I thank Peter again, and please come on out and have a coffee and some cookies. Yeah.
Thank you.